And I always find it ironic that doctors are very comfortable with family history and bringing that into, right, diabetes, but they're scared of genomics. Yet genomics is probably a much better measure, if you will, of what's there in your genome that you should be worried about, not in family history or something. We use those together, as quite frank. Okay, the other thing that was a big deal that popped up was this one: increased risk of type 2 diabetes from a 26% to 47% chance. And I'll jump to the punchline, which is it turns out I got type 2 diabetes during this study. And it was a big surprise to me as much as it was for others. So it was this day here, I went in for a fancy glucose metabolism test. And the woman looked at me and said, "No way you have type 2 diabetes. You're not a family history. You don't look it." It's a very typical comment. And it said, "Yeah, but we sequenced my DNA and we wanted to look for this." And so this is just my fasting glucose, 127. That's high. It should be in the 90s, which is where it had been until then. So, because remember, we've been following all my ohms, my metabolome, my glucose is one of those things. So they're running along normally. It was high that day, and I was borderline for insulin sensitivity or resistance. I went a week later because this was high, I got another measurement, came out even higher, and this is a better measure of the steady state glucose. It's arbitrary, but the threshold for diabetes is 6.5. Okay? And I was right at 6.4. So I went to my general practitioner because I didn't know anything about type 2 diabetes. It was 5 weeks later, it came out even higher, 150, crossed the threshold, diabetic. I can tell you when that was. It was April 11, 2011, because on that day, I changed my diet from what was a terrible diet, lots of sweets and desserts, including ice cream, could respond to statins, completely cut all that out, doubled my biking, I did biking some, and started running. And it didn't happen right away. It took 6 months to get the glucose back down to normal, which it did, and I didn't need drugs. So I was able to use, in this case, a change in lifestyle to actually manage this. And so this was a big deal at the time because the first time someone used their genome to predict their risk for disease, and they got the disease. And in my case, it was actionable information. Now, a couple of things to come out of this. One is that you'll notice when this happened right after this nasty respiratory syncytial virus infection. And so we made a new guess that maybe viral infections are associated with type 2 diabetes. Stress responses have been shown before, but not viruses. So this is a new discovery, if you will, that we're trying to actually follow up on. And I'll show you later, we have a cohort of 60 people to follow. The other thing I can tell you is that my problems aren't over. Unbeknownst to me, this has to do with how we're running the study, but it actually turns out about a year ago, my sugar went up again, and the information wasn't relayed back to me. So it's a completely blind study, if you will, to the point where it's 7.0, my hemoglobin A1C has been running there for 10 months, actually. Well, it was in the 6th, and then got to 7. And then I discovered that just before Memorial Day, took a few blood samples, and then started running. I don't have a slide of this, but I can actually see now my glucose is coming back down. But even though I maintained the diet, I had stopped running, by the way. And so for me, I can at least manage it by exercise. Now, I always expected this to come back because age is the number one risk factor for type 2 diabetes. I didn't expect it so fast. I thought, 10 years from now or something, but in fact, it came back quite quickly. So, if you will, I've done the experiment twice now where I've seen my glucose go out of whack. In my case, again, I have to manage it using exercise for the moment. And I won't show you this, but my genome tells me what drug dose I should use. Metformin is the leading drug you would use for type 2 diabetes, mine's type 2. And my genome tells me what dose I should start out with, which I did not have otherwise. So anyway, I hope I never need that, but I may, the way it's going. All right, I'm going to jump over to and say this other omics information. This is a research study, but it's been incredibly valuable for understanding what's going on. We can see my biochemical pathways changing during the times I get these viral infections and the times I got diabetes at a level no one's ever seen. You can see these pathways change. Just as an example, this is when I got my diabetes during the RSV infection, this is a time course. These green molecules are all the ones that went down, the red ones went up. And my insulin biosynthetic pathway dropped during this time. It's actually been down somewhat since, if I look across all 4 years. So I'm, by RNA levels, making less insulin. Other things we can see are spikes. I can see this time I got diabetes, I can see lots of things happening. And some things got picked up better with the proteome, the protein measurement, some with the metabolome, and some with the RNA. But the integrative analysis, seeing all these was very, very powerful. It's like getting an IMAX movie of what's going on while you're getting the disease. And so we think this has been very, very powerful. The other thing I'll tell you is that some people say, Mike, what you're doing is really bad. You're going to scare people into getting your genome. People are going to get their genome sequence. They're going to see all these things wrong with them. You're going to lead to millions of dollars of follow-up testing. You're going to scare the jabbers out of them. And this is not a good thing. Sequencing is not a good thing. And so we said, all right, let's do the experiment. Let's look at 12 people just like me. We'll go through their genomes in detail. Very, very high analysis. And what we find is of these 12 people, just as we do with who we were analyzing, we find on average there are 5 changes in DNA that suggest follow-up tests those individuals might do. Or at least 3 follow-up tests, some of them aren't testable. And it's not millions of dollars, it's $400 to $1,400 per individual. It's not free, but decent enough. Here's why it's $15,000 per genome. There's 100 variants you're looking at. It takes about an hour per variant to look this stuff up, these changes. It takes a long time. This can get automated. Here's an area for good company opportunities. Okay, and then one of the things that came out was there was very, very interesting in general, but this one's particularly powerful. There's a woman in our study who did not have a family history of breast or ovarian cancer, but she had a mutation in BRCA1, which almost invariably leads to breast or ovarian cancer, and greater than 90% of women who have this will get cancer in early age. And in this case, it's very clear it's an inactivating mutation, and based on this information, this woman opted for surgery, basically. So the net result was her genome information was very, very valuable to her, we would argue, for healthcare. Now, how you decide to use that information is up to you, but at least we would argue this is good information to have. I'm just going to jump ahead and say the genome is really just the start of this whole area. There's lots of other areas we should be adding on. Methylation is a way of measuring epigenetics. You may not realize this, but you can tell a person's age by which particular genes are modified by DNA methylation. It's called the methylome. And we can actually integrating this into healthcare where we basically can look for changes at 5 loci like this where one of my alleles is knocked out by genetic mutation, another is knocked out by DNA methylation, which normally silences genes. Okay? And so we can actually pick up situations like this, and this predicts these genes should be inactivated. You would never see this if you only did genome sequencing. Forgot to say your methylation pattern is affected by the food you eat, it's affected by your age, and probably lots of other things. We don't fully understand it yet, but this is the kind of information we're trying to bring in. We're letting the data tell us what's going on. The other area that we think is incredibly valuable, you may have heard a lot about this, is the microbiome. Okay? This is what I was saying about before. I had this double infection. I had a rhinovirus infection this time here. And then 9 days later, I had a fever again. We were trying to figure out the virus, and we never did. But then later, when we were actually sequencing all the microbes from my nose and from my stool, everywhere else actually, we discovered that from my nose. It turns out, the time here's how here's when I got sick, the second fever, and then as I'm recovering. The bottom line is it looks like a streptococcus infection. Probably the most expensive way in the world to figure out how to All right. What was powerful about this is we did these same time points for my stool, and what you'll see is that your microbiome changes completely, or very extensively, I should say, in my stool, even though it's a nasal infection. These are systems-wide effects. We don't fully understand how they're working and what's going on here. This is the goal. It's letting the data, catch the data, let us tell what's happening. And so the overall goal is to really roll this out on lots and lots of people. So we're bringing in other kinds of measurements. You may notice I'm pretty heavily wired here. I have a jawbone, a basis, and I just got this tom-tom. I measure all the steps I take by these 4 different devices now, including Moves app. To measure my electrocardiogram right off of the iPhone with this, basically it's called the LiveCore app. I don't have any stock in any of these. That's my electrocardiogram right there, 71 pulse. So you can actually make lots of physiological measurements. And so I'm a believer that we're going to be bringing lots of sensor information, wearable sensor, and other sorts of information as well. This is a subset of the devices that actually I'm using. And so sleep and these other measures are going to be very important for integrating as well. And you might think, well, Mike is just a fluke. Well, I've lined up 59 other flukes just like me. So we're actually going to profile them. There are pre-diabetics, most of them just like me, and we're actually following 60 people now, probably about 70, for 3 years just like me, to to try and understand the effects of what happens when people get ill, what happens to all their different systems, and just stresses in general. One of the sub-stresses we're doing is we have a set of people who are actually undergoing a weight gain, a weight loss study where they actually overeat, if you will, for 30 days, gain weight, and then actually lose weight for 60 days when you follow their process as well. So it's one of the perturbation experiments. Right? So the goal is to really understand what's going on with these various perturbations, and most importantly, do it at the individual level. Because we think what's powerful about all this is not understanding in general what's going on, but for you, what happens when you get a stress response, whether it's a diabetes, trigger, a viral infection, what could happen to you and what we can predict out of this. And so that's really the ultimate goal. And so it is a lot of data. This just shows some of the data we're collecting on me. So genome's about a terabyte, maybe half a terabyte now. And then this other stuff, depends how deep you go, but on me we go pretty deep. So it's about 6 terabytes of data per sampling, plus 1 for the genome. And now maybe by the end of summer, just right at the end of summer, we have roughly a half a petabyte of data just on me. Okay, so we're going to have a lot more too when we have only 60 people. So it's a lot of data, but it's actually not so much when you compare it to eBay or something like that, which has a lot more. But it's a different kind of data. So this is my role in the future. I'm a believer people get their genome sequenced before birth if they want. We're bringing other kinds of omics information, probably not billions of measurements for a clinical test, but something on the order of tens of thousands or at least a few hundred. Bringing other kinds of sensors and monitors, and use this to move medicine from being this reactive stance where we find people get sick and treat them, to proactive where we predict disease or at least catch disease early so that you can in fact manage their health properly. It's huge. The whole infrastructure is not properly set up for this in the US, and that's really where the biggest problem is going to be. And then we'll also have iPS cells and other cells as well. So because I'm late, I'm just going to say that genome sequencing and other omics is here. It's going to be very valuable, we think, for monitoring and dealing with people's health care. This is a very important point I mentioned before. Every person's profile is different. So at the end of the day, you want to see what happens when you get sick relative to your healthy state. Not what does your sick state look like to everybody else's healthy state. That's just hard to interpret, and I don't know how to interpret that. And so at the end, I think we want these longitudinal individual profiles. And lastly, this is really, really important too. You're responsible for your own health. No doctor is going to, what's 15 minutes can help you in these sorts of scenarios. And they don't already, right? If someone's seriously ill in the family, at least in my family, what happens is they call me up. What do I know? Nothing. I'm a PhD, right? I don't know anything. So they call me up and say, Mike, such and such is happening. So I do what everybody does. I Google it and then start figuring it out. Now, I have better connections than most, so after I learn a little bit, then I go around, and this does happen, right? So and then I try and figure it out, and then I put them in touch. But at the end, you have to spend a lot of time on your own health, and if you're going to count on somebody else, it's going to be in trouble. So you can get my data there. I could probably refer to it. I will say, if you like any of this sort of thing, here's a little ad that the genetics department is launching this program in genetics and genomics. I'll have quite a bit of personalized medicine in here. We literally launched it 2 days ago, September 1st. So you can take these classes online and learn something about genetics and genomics. You can take the whole certificate program, which is some classes that interest you. And so this is literally rolling out right now as we speak. So give you more information. That these are people who did the work. And I always like to thank my mom, because when you get your genome sequence, you go back to your parents constantly to learn about what might be in your family history. So I think it ran way over. I'm sorry about that, but if there's time, I'm happy to take some questions. So, yeah.
So you alluded to the fact that that HIPAA is kind of keeping us from getting some data. Is the reason for HIPAA that we have an insurance company that could do something with that data, like to deny you? Is that the whole reason behind it?
Well, it's really meant
to... Don't we have a legal system that says that they can't use that information?
Yeah, you're mixing two things. So really the goal of HIPAA is to protect the subject, to protect the individual. But we're in a whole new era that HIPAA hasn't quite caught up with, which is a lot of people want access. Like, I can't return information from the study to the subjects unless it's been done in a CLIA lab, which is a certain kind of testing. There's no such thing as a CLIA microbiome, So they won't let me return information back to subjects, yet the subjects would like to, I'd like to. And we genetically counsel folks and things.
Protect
So
them
it,
from what?
well, the idea is you might learn information about yourself that is harmful. So a lot of, it's the way our whole medical profession's trained. So I'm gonna now insult a lot of people and get some shoes thrown at me, but the way we train our doctors is from we're in charge and here's what you should do, and that's just not how to manage things. The information's too much. So, and you can't do it in 15 minutes. So it really has to move to, and it is shifting some to a more cooperative fashion where here is, here's the information, here's what you should think about. So, but right now, a lot of people, especially when I was saying we're going to sequence people's genomes, they absolutely didn't want us to do that because they were so afraid we were going to scare people with this. They think they're not ready for it. It's this idea that they know best for you. And we've got to shift away from that and let the consumer decide. So here's where I do agree with 23andMe in the sense that who owns your genetic information? You do, and you should have a right to it. What might be a little bit different is I do think you should be counseled about what that means. That is to say, we sequence your genome and you may have, probably not if you had it, but Huntington's disease. But we could tell you what kinds of information would you like back. You may not want to know if you have an incurable disease, but that should be your right. And there's some gray areas hard to decide what you might tell people, what you might not. But for the most part, it's pretty obvious. But again, if that's your decision at the end, I'm a believer that if I want to know I'm Christopher Huntington's, I should be able to get that information. And so, again, not everyone agrees with that. Some people think, well, you think you know, but I know better than you. So this is where some of the problems surface. So that's from the genome side. On the insurance side, so right now you can't be discriminated for health or employment. There's a non-discrimination, Genetic Non-Discrimination Act. But you can be for life insurance and long-term disability based on your genetic information. So there's still some holes there, but it's not, so that's where we are with the insurance part. So my own view on the insurance, though, is that the insurance company should pay you to get your genome sequenced because you would manage your health better. But our healthcare system's screwed up. It doesn't have the right incentive for this because we change our healthcare every time we change a job. And so why should an insurance company pay you to get your genome sequenced when 2 years later they would be with somebody else? Whereas the socializing countries have a much better, socialized medicine countries have a much better opportunity to implement this sort of thing in Europe. And this is where it's rolling out. They're now talking about 100,000 genome sequencing projects as part of the UK system. And others where they can actually implement this and people are with the same system, if you will. So, but I think it is somewhat catching on. Kaiser and Geisinger are starting to think about these sorts of things and they're bigger systems. We'll see what happens. Yeah, I guess you're next to the microphone.
Hey, who has the microphone with? Great presentation. So I was struck by this idea that a lot of important sort of variants have been discovered by a combination of a discerning individual who's motivated and a bunch of luck. I remember a story about some a doc who found important variant for fatty liver disease and found the genome was responsible and so forth. And your discussion with a mother who found a problem with her child. And I'm an interface designer. I'm trying to figure out what are the components to lower the barrier or to improve the odds, so that the pieces are on the board, not relying on a blog post or an insightful physician in Texas to find the kind of connection between the problem and the source disease.
Yeah. So it really comes down to sharing information. The more you can share information and the higher quality it is, the better you'll be. But the privacy issues, even though I kind of played it one side, they're real. That is to say, someone could look through your genome and say, well, you're Alzheimer's, you're APOE, E4, so you may have a higher. If you're homozygous, you have a 60% chance of getting Alzheimer's as a male.
Right.
So these are some of the issues that someone could discover out of yours, and so and say, well, we're only going to extract that little piece of information out of your DNA. That's not going to work. So anyone who knows genetics will be able to add that back in and say, well, here's what he's got.
Right.
So this is these are real issues. So you have to be willing to share that. Now, again, in these situations where parents have a child who's got a serious problem, privacy goes out the door. They want to solve their kid. I'm just reiterating that. And so I think in those cases, it's a no-brainer to share the information. But again, I would argue it's up to the individuals to share the information. And of course, I think the less we would discriminate against people, the reality is, by the way, we all have mutations that say we got problems. So if you think there's a clean genome in the room, you're mistaken. We all have mutations that put us at risk for something.
I would just say,
So that's why sharing it seems to me, it's kind of like, when people show up at parties, say, well, I got a backache today. Or soon we'll say, well, I got a frame shift. Such and such.
I would just
shift the dialogue.
it's where you share. It's practical side of it. Share it meaning what? It's the interface. What's the thing?
Well, you could envision a Wikipedia kind of thing for each gene in the genome or for each disease. Getting good clinical phenotypes actually is going to be a big deal, because understanding that my disease is like your disease is where a lot of these matches are going to get made. And they may be made differently. If they haven't been diagnosed exactly the same way. This is why I like the omics profile, because I actually think those measurements are a lot more precise, they're a lot more quantitative than someone saying, well, you have intellectual disability based on what they could garner from a fairly short test. And where are you on that whole spectrum of things? That's just a lot harder to quantitatively decide. But not that, at the end of the day, intellectual disability is probably going to be 100 different diseases as well. So, saying all these complex diseases, diabetes is not one disease, it's probably 100 diseases, same with autism. So we've got to break them down with molecular probes, and then I think we'll also be able to share and make these matches better too. So, I think there's a bunch right there. Okay, this one in the back.
Yeah, you mentioned Huntington's, and so there are all these diseases where you have a certain likelihood of getting a disease, and then the probability is really high. Now, with all the advances in genetics, as I understand it, there's a lot of progress in identifying whether you have a likelihood of getting something or not. But then, if it was a bacterial infection, you do something to get rid of the bacteria. But with things that are genetic, as far as I know, there's nothing that can be done to get rid of whatever the defect is. And if anything, in half the cases, there's nothing much that you can do. And so any comments on that?
Well, it depends on the mutation. I mean, you're right. You don't typically go in and correct the genetic change. There are some diseases there are trials with some of these things, mostly in the immune deficiency area, where people are trying to correct the mutation and have had some success. It's a very small number of individuals. But in general, there's some areas where it's a no-brainer. You may not realize it's not an issue anymore. PKU. We now screen for that in newborns. Standard test. Just look for the metabolites. You see the problem, you change your diet, they're fine the rest of their life. If you don't catch that, and you wait several months, kids start getting brain damage, irreversible. So, but now it's routinely screened for, so you catch the defect, things fine. So there are cases like hemochromatosis, which is an iron uptake deficiency. There's another case where, again, you can control the diet. So I think there are cases where you can. There are cases where it's tough. Huntington's, nothing you can do. Parkinson's, maybe a little bit you can do in area of interest, at least short-term things you can do. But these are things some people would prefer not to know. And if you're in that category, that can be your decision. Okay? I don't want to know about my Parkinson's status. And it should be your right to know or not to know. There are a lot of people, by the way, a lot of women who have breast cancer in their family, choose about 30%, choose not to know. They could get a test for BRCA, which is the one that was common, BRCA1 or BRCA2, on the gene. And they choose not to know. That is their prerogative. I personally think it's better to know, so they could either get the breast and ovaries checked more frequently or have surgery should they so desire. But that's valuable information because a very high probability with a damaging mutation of BRCA gene, those individuals will get cancer. So I would argue that information, yes, it's fatalistic to get cancer, but it actually is actionable information, even for the BRCA case. So So it depends on the gene mutation.
Are there established correlations?
We'll do you and then you next. Okay, sorry.
Sorry.
Yeah,
Sorry.
go ahead.
Any established correlations between the omics and things like depression? I mean, because you take that to the extreme, there's Huntington's and Alzheimer's, but
Yeah, so I'm not sure I've heard Alzheimer's linked to depression. It may be. There's no question there's a genetic component to depression. These are complex diseases. Even Alzheimer's usually is a complex disease, and it probably is multiple genes involved. And when people have started mapping this out, depression is much less mapped out than, say, autism. And for autism, there's 300 some genes implicated. Each has an incredibly minor effect. So no one gene says you're going to get autism. We've actually been trying to put together pathways that do this, and we now have a pathway that's very suggestive. We can see it highly rich in kids with autism. They have more mutations in this pathway in general. So I think that's actually only half the equation. The other half that people keep ignoring is the epigenetics. It's the fact that with nutrition and these other things, you are actually affecting the activity of your genes. And beyond your genes, probably RNA and other ways as well, then that has an effect as well. That's why I just think the genetics is just part of the equation. It's the one we go after now because we can. The epigenetics, I think, is going to be valuable for the future. And we can do screening in certain areas really easily, like your blood and skin biopsies and things like that, but nobody's going to go in taking brain biopsies for autism tests, right? So you have to sort of think about which test will work where. And we don't completely know. So autism in some cases may be very brain specific, in other cases may be systemic throughout the body, and those latter ones you might actually find. So I'm meandering a bit, but you can see the complexities here. So multiple genes, multiple effects, and challenges in diagnosis. But I looked at those as those were obviously areas of opportunity then as well. If we had them solved, they would have been solved. If they were easy, we would solve them. So I think over here.
Yeah, actually, two questions. One is, how has your thinking evolved over the last, say, 10, 15 years in terms of the deterministic capabilities of genomics versus what you just mentioned, epigenetics? Like 10 years ago, you might have said X% of the outcome is determined by genomics versus today. Like, how has that changed? And then this follow-up question is, in terms of the omics profiling, I'm sure you've done the math of how many profiles you need to build a reasonable model. It sounds like you're tracking a lot of things. I don't know how you control all that.
All right, let's see. Well, let's start with the latter one. I don't know how many I need yet because I don't know what's the right markers for the right disease. But I do know there's a world coming where there's going to be 1 million electronic health records linked to 1 million genome sequences. And that's not 10 years away. That's like 3 years away, maybe less. That's not far. Who has access to that will be a very interesting situation. But that's going to be valuable. Now imagine adding 1 million of these omics profiles like mine on top of that. You'll be able to correlate diseases and phenotypes at a level with genome sequences. And I think that answers the question. And I don't know. I don't think we need billions of measurements to predict the top 100 major diseases people are going to get. But I don't know which of these billion measurements I do need. I do know I'm going to die of something someday. And I'm going to be profiled, I hope, up to that point. And if it's a slow chronic situation, I want to figure it out and see what markers are there. And if it's a acute thing where I die quickly, somebody after me, I hope, will be able to use that information and say, there was a biomarker for Mike Snyder. If we'd have seen that, we'd have known he was going to be stupid and walk in front of the bus or something. So that's how I want to treat the data. I want to let the data tell me what's important. And because there's so many different diseases I don't know, we all get multiple diseases too, some of which may be linked, some of which may. So that's the second part. Now I forgot the first one. What was that? Oh, how much is genetics? How much is epigenetics? I don't know. It's probably true. I used to think we were a lot more hardwired than we are, meaning we're very genetic, and I still think that's true. We are pretty hardwired in our genetics. Anyone who has kids, right, probably comes to that conclusion. But I do think there is room for epigenetic modifications as well. And I think as you try and solve some of these diseases and realize you can't figure it out, it means it's either complex genetics or it's genetics plus environment. So I think because we've failed probably more recently than we've succeeded, I've now started thinking about the power of epigenetics more than I used to, I'll put it that way. So it's a fair question. Yeah, I'm not sure who's next. Oh,
Yeah.
yes.
So I wanted to, you did your this experimentation on diabetes and yourself, and you showed that when you did this genetic analysis that you were pre-diabetic and certain percentages came out. When you went through that diet change and exercise, did you go back and look at the statistics, whether they actually improved or they were exactly the same?
Well, my genome hasn't really changed much, or I haven't really I've sort of resequenced, but I've done my methylome now for the last 4 years, although it's still analyzed. There aren't big changes in general. I knew that anyway because I had sequenced my blood and saliva, and they were too different. But, so your DNA doesn't change, but your, I mean, it is true my profile has changed some. I'm still trying to figure out what parts have changed, what parts haven't. I have noticed that, as I mentioned before, my insulin RNA has dropped from when we started the study to now, and that's been kind of consistent. So that never came back, even when I improved my diet and things. So some things may be more permanent, or maybe that's just an age factor too, whatever that means. See, I don't like that phrase I just used, with just an age factor. What does that mean to be an age factor? It means something has happened biochemically, and I want to figure that out. So anyway, these are the issues that we're dealing with. So, and there's just more to pour over. I think I can see some pathways change. I can tell you we see some very interesting bursts after some of these infections no one's ever seen before by doing this profiling. So we're learning new biology that happens during viral infections, again, at a level. So I can see some of that kind of stuff. How things have changed on a more permanent time scale, we just need more analysis. I guess it's still in progress. The analysis is by far the slow step here. Okay. Yeah.
Earlier in one of the cancer slides, there was something mentioned called genome maintenance. What is that? Is that like lengthening telomeres or something?
Genome maintenance, yeah, I don't remember, so the question is, one of the slides had something about genome maintenance, and I have to admit I don't remember what that one was. It was, anyway, genome maintenance would be your telomeres, it would be your like ovarian cancer happens, the BRCA is mutations are involved in DNA repair, which we call recombination. And if you damage, if one of those genes is missing, you actually have more mistakes and more problems show up with your DNA. You're not maintaining your genome in an intact state. Integrity gets damaged easily. So yeah, some of these maintenance things are for maintaining the ends of your chromosomes. Some are for just maintaining proper repair in general. So that's important for cancer for sure. Yeah.
Besides you guys, is anybody else doing these personal omic profiles?
Yeah, so, well, Lee Hood has just announced that he started a project very similar to this. Which I think is great because we're going to wind up with a lot more of these. George Church has a project where he's basically set up a website where people can send, and now some of them are getting their genome sequenced. He hasn't really set up the omics profiling, but he's very interested in this space, and so I've certainly given him all my data, which he'll link up on his website, and we'll see if others in my study do as well.
But
So,
there's no clinical use of this?
not just yet. It really is a research study because we have to pull out validated biomarkers. In our case, I think it's panels or pathways that are going to be the biomarkers, not individuals. And I think that's what will lead to the robust test. But we're not at that point yet. We have very interesting things we see. I can tell you times when I got diabetes, and actually when I got sick, my neuroendocrine pathway is changing. Very fascinating. So I think there's something to that, but I don't know that that turns into anything clinical yet. This is the kind of information we're getting. This is why it's a research study and not a clinical one. At the end, I hope we'll just zoom in on somewhere between 200 and say 20,000 markers that will measure your health state incredibly robustly. And in my world, that would be a home test you'd do every month. You just prick your blood. We're doing this now. If you prick your blood, you can measure glucose, right? That's what people do. We can now measure 900 things out of that same blood drop. And this is where I think the field should move. So you could actually do a home blood test. And so typically, I don't know about you, but I used to go to a doctor once every 3 years as a healthy person. And that's just too infrequent. If something bad happens, it's just not enough. And this is why I think we need these frequent home tests. It's not going to replace going to a doctor, but it'll let you catch disease early if you have a panel of biomarkers that you can do readily. And I think this is space I would like to see developed enormously. So home tests.
I want to hear your comments about gene patenting and mutation of genes and patenting issues related to that.
Well, since I founded a company that sequences genomes and interprets them, of course I like all the information freely available. I mean, there's no question this is for the public good to be able to do that. You know, it used to be, I understand why Myriad did what they did and others, because it was a lot of work, right, to go in and find these mutations and set up the test. And so certainly in that era, it made a lot of sense to patent genes and things. So, I just think we're getting probably past that time. That is to say, your genome is your genome. It is a lot more public. So that part, I'm generally in favor of being open and available for the gene parts. For some of the diagnostic tests and things, I think the way the patenting rulings has gone have been very strange, in my opinion. If some things are natural products, they're getting hard to patent now, even if a company might have spent many years trying to get to that natural product. And so I find that would de-incentivize people to find natural products that might be very effective. So that's not gene patenting, but you get the idea. So I think when it comes down to natural things, I think there are times it is useful, I guess, to be able to patent them, is what I'm saying. If it's an entity. For genes, I personally prefer that they're not patentable. So I think that serves the public more good overall. That's where I stand.
Thank you for the talk.
Sorry.
There you go. Sorry.
You mentioned several times 23andMe, and as far as I remember, the current going price for sequencing